For our next paper, Maximili Bacher is correct. Bacher. I have to learn more the names. Yeah, with the from Carlos Institute of Technology, Germany, automated value-oriented forecasting model selection by meta-learning application or dispatchable feeder. Thank you.
So thank you very much. Okay, I will a little bit hurry because I have too much slides for the short amount of time to present a paper. So I'm Maximilian Beichter. I'm presenting for my colleagues and myself our work on automatic value-oriented forecast model selection by meta-learning, an application on the dispatchable feeder. So first I want to start with a short motivation, and I want to introduce two terms that are very important in the context of the whole presentation. So if you think about a building, you can, for example, forecast the PV installation installed on a rooftop, or you can, for example, forecast the load and a load of the residuals living in the building. If you think what is a good forecast, what would you do? We already saw competition-wise, normally we use, for example, forecasting metrics. Forecasting metrics, we now say that is a measurement we call forecasting quality. But why are we doing forecasts? Forecasts are normally done because we think about, okay, we want to use that forecast, else it would be absolutely stupid to do a forecast. So think about, okay, afterward, we are doing something with it. An optimization problem, for example, a building management system. This has a feedback loop to the house itself. So we are thinking about, okay, there is something like an value of our forecast. This value does not really in every case depend on the metric we early accessed, the forecast quality. This value could, for example, be different and in nonlinear dependency on the forecast quality. So we consider this term, and looking at more the optimization perspective of on the forecast as the forecast value as the value of our forecast in our problem. So forecast quality, the perspective of the forecast itself. So absolute errors or something like this. Forecast value, the perspective of the optimization problem, and using the forecast in a downstream application. So yet we think about, okay, we have a variety of forecasting models, and which model we should take to get the best forecast value, because that's the thing we want to maximize. So that's the agenda for today, or a short agenda for today. So I will simply show a very simple meta-learning framework for forecast model selection. Then I will show shortly the dispatchable feeder problem we use, and afterwards I go shortly through the analysis and the results and make a conclusion. So we start in our proposed framework with data. We have some forecasting models, we have an optimization problem, we have a building, for example, in our case, and what we can retrieve with doing forecasts, doing solving the optimization problem and playing the game, like simulating it all the time, we can retrieve forecast values. So we can retrieve the costs that are taking place in the real world. On the next thing, we also can retrieve data of the buildings, because we know what the data is about. We know the building, we know how much PV is installed, and all the things we can, for example, get through the data. So we can retrieve two things, the forecast value and the metadata of, for example, a building. Yet we can, for example, as we can do this various times with different forecast models, through different buildings. So we have more than one dimensions. In this case, we have, for example, more buildings and more forecasting models. And afterwards, we can have a lot of tuples like forecast value, metadata, and this we can formulate in a kind of classification problem. If we think about, okay, this classifier now says us, if you want to forecast for this optimization problem regarding this building, you should choose this forecasting model. As you can see, this classifier could afterwards be applied on, for example, a new building, retrieving the metadata of this building, and then choosing the right forecasting model for your optimization problem. And therefore, you can retrieve a better fitting forecasting model with respect to the new building. So I will now introduce shortly the optimization problem we use. This is, we call it the dispatchable feeder. It's a building with an inflexible energy demand, so no demand side demand response is here taken. So we have people living in the building, they're having their residual load. Further, we have an PV rooftop installed. So we have kind of a PV power generation. So, and in addition to this, we can use a battery to store energy, store excess energy, but, and that's the most important thing, this dispatchable feeder can also interact with the grid. So for the grid operators, it's like a little bit with uncertainty. What will the dispatchable feeder do in this case? And that's the reason why the dispatchable feeder in this scenario is forced to use its opportunity to dispatch. This means we say, he's giving us 12 o'clock in the dispatch schedule for the next day. And I will say, I will consume that much energy or that much, consumes that much power through the next day or give that much power to the grid. And if we hold this and we, for example, submit this dispatch schedule and try to follow it in the next day. So how does this look? If we look at there are two stages. Okay, we have a first level stage using some deterministic forecast of the presumption for the next hours, for best case the next day, and therefore we calculate the dispatch schedule. In this case, we want to minimize our costs, which will our consume of energy will take us. And the next day, as we are constrained to this dispatch schedule in the online phase, we have to follow the schedule. We have to try it at least, else you have to pay. So we think about a system where we, in the second stage, on the day, we are following the schedule as good as possible to minimize the imbalance costs. So this is the optimization problem mathematically in the paper with a lot of time, easy to understand, but not for a year and maybe for another discussion later on. Okay, we are back to our framework. We are back to the thing like we have a lot of simulated this scenario, and now I will go through the analysis and which part we varied to make the analysis. So first of all, we try to forecast the presumption. That's the beginning of our dispatch schedule generation, and forecast this presumption with different loss functions. What does different loss functions mean? If we, for example, use an MRE, we always get the median. If we use a mean squared error, we get the mean. If we use probably a pinball loss, we get a quantile. So we used different kind of loss function, a very basic neural network model, but a variety of different loss function, which could be maybe beneficial for the downstream application. So this is the first thing we varied. The next thing we not varied, in this case, we use for evaluation is the forecast value. Our forecast value are the total costs. So these total costs are partial of the dispatch schedule cost plus the imbalance cost with a factor. So we can, in this case, lead to a higher requirement to follow the schedule. Further, we have some statistical building informations. So in our case, we use all the statistical building informations, additionally a profile of the presumption of the last 2 years and the transformation with PCA and the standard scaling. Further, we also varied a little bit on the classifier choosing. So here is the list of the classifiers. Okay, I'm good in time. Perfect. As you can see, we varied a little bit with the sklearn library these are the classifiers that are available. Further, we also got, of course, different training and test buildings. And how we use the data we are using with the Auscript data set is 3 years of residential load and PV generation. And we varied the data by buildings with very different characteristics. And because we scaled, for example, the PV, and we scaled the load with different factors, so we made a much more extended data set to provide more variety in the data in terms of many different buildings. Further, of course, to ensure a good data split, we splitted the buildings along the building dimension and along the time dimension to ensure data independencies for our test and validation and train splits. This more in detail you can also retrieve in the paper. So what should be the benchmarks? So going more in detail with the evaluation, we should think about what could an easy benchmark. Okay, the first thing, maybe the median or mean is already the best thing we can do. So simply use one loss function for the building. Simply through all our test building, use one loss function. For example, the MAE, the MSA, or arbitrary pinball loss, or something you already saw. Another option could be, okay, we have 2 years of data. Why don't play the game with, okay, we can simulate this thing. We can think about playing the game a lot of times and then simply pick the best working solution the last 2 years and then calculate it based on it and say, okay. So that would be another option. So that would be a very tailored option to the building, but maybe also a very computational difficult thing if you have to do this for every building. So that are the 2 benchmarks we take into account. Also, that are the metrics again, our already known forecast value, and for the classification, in this case, we have also used the F1 score. So looking at the results, okay, what we can see? We can see if we look at the one loss function column, maybe we should, in order to keep the time limits, only focus on the imbalance factor 2 column here. If we look at the one loss function, we see, okay, MIA seems to be okay and good solution, but we improve with manually selecting. So there are buildings existent which not benefit from the mean absolute error. So manually choosing the loss function leads to an improvement. Our framework, choosing the loss function by classification, leads to less improvement than manual selecting the loss function. Okay. So is this completely stupid, the whole method? Maybe not, because as we also varied with the classifiers, so we can see some classifiers perform better and some classifiers perform worse. As you can see here, we choose the support vector classifier. And coming back to, is this a good idea to do this as a classification task? And we say yes, because if you think about having a much higher variety of loss functions, for example, having much more loss functions and for example, having much more buildings, you have to compute every time the completely optimization problems for every loss function you want to search in your search space. So it's, in our case, we would have taken to the first forecast on our CPU and hardwares, we needed 287 seconds to manually select the loss function. After the classificator is trained, you only need to pick the loss function the classificator gives you. This is maybe shown already a good choice. So therefore, we say, yes, we couldn't reach the result of the manual loss, select the manual loss function, but we could, by using the framework, reduce the forecast model selection time massively. And that leads me to the conclusion. Our proposed frameworks reduce the costs and improves the accuracy compared to selecting the same loss function at the same time on every building. But And our proposed framework leads to similar cost or comparable cost and accuracy, requiring much less computational effort. Future work could, for example, be incorporating a dynamical selection of the forecast model, for example, doing this on daily basis. For example, thinking, okay, which state of my system is now there, which forecast model I should take. Or further, it could increase, we could increase the considered set of forecasting model with much more diversity in the forecast, which leads to much more properties that may be beneficial for this downstream application. So, 50 minutes are gone, and I thank you for your attention, and I'm happy to answer your questions.
Thank you, Maximilian. Some question from the audience? Okay.
Thank you for a very, very nice and interesting presentation. But I'm wondering why. I understand the improvements you suggested to have a dynamically optimized thing, because when we consider this scheduling, the penalty is typically varying from day to day. So the asymmetry in penalty links directly to the quantile, which is optimal quantile, right?
For example,
So for instance, and for instance, if you're considering the battery size and have a battery like the example you showed, it's the autocorrelation in errors which are important. Because if you typically have autocorrelation in forecast errors,
yes, of course.
and if the errors are on the same side,
Yes.
and you need a bigger battery if they are independent. So can you comment upon how you? That's why we prefer to have the forecast model as a full forecast model, where we instead of this score function are using the CRPS or the Varigram score, because then you consider autocorrelation and the full stochasticity. But maybe that could be a next step or something. Or can you comment upon that?
Yeah. Okay. I will answer this question, or not question, more a remark, I would say, with a lot of information, maybe a little bit more of information. Okay. First of all, a stochastic version also exists of this optimization problem, and there is something like this more covered. But there, with the probabilistic things, you have to think about other properties. You have to think about sharpness, calibration, and all those things that can maybe also influence your forecast value. As you normally, CRPS is a mixture of sharpness and calibration in these terms, and therefore you have kind of, that will also be very difficult. But with the autocorrelation, that is a really interesting remark, and I will take it with me and need to think about. Maybe we can talk later on.
We can talk about later, because for the correlation, the Varigram score is
I know that could be a problem.
Yeah. But thanks a lot for a very, very inspiring presentation.
Thank you for the contribution, for the question. Thank you, Maximilian.